Okay, so in that case, thank you so much for being here, and please go ahead. We'll go for around, let's shoot for 40 minutes.
Okay, great. Right, so today I'm going to talk about new work on linear time zero-knowledge succinct arguments. And this is actually based on two recent joint works. The first, which appeared recently at TCC 2020 with Alessandro Chiesa and Jens Groth, and the second, which is just about as brand new and fresh as it's possible to be, appeared on ePrint yesterday, I think, and that's joint work with Alessandro Chiesa and Sichi Liu. Okay, so we're in the setting of efficient zero-knowledge arguments for NP. And in this setting, a prover wants to convince a verifier that a statement from some language is true. So for example, that an n-gate arithmetic circuit over a finite field is satisfiable. And we can ask ourselves the question, what are the best possible efficiency parameters that you could achieve from such a zero-knowledge protocol? So if the circuit has n gates and it's over a finite field f, then maybe the best that we could hope for the prover and the verifier is a linear number of field operations relative to the size of the circuit. I mean, certainly both the prover and the verifier, they do have to read the circuit before they can go through this protocol. So that seems reasonable. And then we could hope for just a polylogarithmic number of bits communicated between the prover and verifier. So is this the best possible? Well, maybe. If we introduce an indexer to pre-process the arithmetic circuit for the verifier so that the verifier doesn't even have to read it, maybe we could hope to do even better. And we could go for polylogarithmic verification time, for example, with the same nice linear prover time and like nice polylogarithmic communication complexity. So in some sense, you might consider efficiency parameters like this a holy grail for efficient zero-knowledge arguments. Now, just to be very clear and explicit about it, let's talk about what counts as linear time for the prover and the indexer. So the original computation that we'll deal with in this talk is the computation of an n-gate arithmetic circuit over a finite field, as we've seen. And you can evaluate the entire circuit using n field operations. So what kind of prover and indexer computation should we allow for linear time? Well, anything with like a small logarithmic factor or any like small multiplicative dependence on the security parameter, that's going to be completely disallowed. We don't want that. But we would allow something which is, a constant times the number of gates in the circuit, maybe with a small additive dependence on the security parameter. Now that would be okay. So that's what counts as linear time for the purposes of this talk. So unfortunately, lots of prior works fail to achieve, this really, really strong requirement from zero-knowledge arguments. And the main reason for this is because they use techniques like fast Fourier transforms to perform like polynomial multiplications as part of the proof, or to compute encodings of the witness using Reed-Solomon codes. And this just adds an extra logarithmic overhead into the prover time. Or alternatively, there are plenty of works which are using algebraic commitments like Pedersen commitments. And initially they look like they might be linear time, but actually to compute a commitment to a linear number of values is a linear number of exponentiations in some kind of cryptographic group. And then that gives you a lambda overhead when you actually examine that cost and measure it in terms of finite field operations. So anything that uses fast Fourier transforms or the most popular algebraic commitments like Pedersen commitments is just completely ruled out if we want this type of result. And there are lots and lots of, really exciting, like really, really good, concretely efficient existing works, which just falls short of this holy grail. And lots of them have actually eliminated the fast Fourier transforms completely, but they still rely on these cryptographic commitments, even though they achieve like excellent proof size and like really good prover and verification time in practice. If we want to achieve this holy grail type result, then for sure we need to throw away the algebraic commitments and FFTs. So what should we do? Well, there is somewhere we can start from. There was a result in 2017 which actually did produce cryptographic arguments with a linear time prover and a linear time indexer. And that's based on, first producing an information theoretic protocol, an interactive oracle proof, which has similar nice linear time properties. And then there's this hashing strategy, whereby all the elements in this information theoretic proof are kind of hashed up into a Merkle tree. And then this gives rise to a cryptographic argument with similar efficiency properties. So the key point here is that the hash functions used for this transformation are a bit special. So hashing a linear number of field elements is actually at most a linear number of field operations. So this hashing strategy is really good. Unfortunately, we don't really get the result that we want because the underlying IOP has a verifier complexity and a query complexity, which is still a square root in the circuit size, unfortunately. So to achieve our holy grail, the question becomes, can we construct linear time IOPs with better query complexity and, of course, better verification time? So now on to our results. And it turns out that the answer is yes. So over these two recent works, in the first work, we actually managed to get an IOP which has better verifier and query complexity. So any sublinear value in the size of the arithmetic circuit, which is really good. But we didn't manage to get any zero knowledge properties in that work. Then in the second follow-up work, we actually managed to shrink down the verifier complexity and the query complexity to polylogarithmic and logarithmic and really get this zero knowledge property. So this is great. This kind of gives us the holy grail that we always wanted. If we follow the same hashing strategy, then we get some cryptographic arguments which have exactly the same corresponding efficiency properties and zero knowledge properties. So yeah, fantastic. We're all done. Well, there are still some some small things that we'd like to improve about this result, which are pretty interesting in themselves. So I think the main caveat that we have here is that the argument works over large finite fields which have at least big omega of n elements. So I'd say this question of linear time arguments is still open for really small finite fields like constant size fields, Boolean fields, and so on. The other thing is that the verifier complexity and the query complexity is still polylogarithmic and logarithmic. Maybe we could also aim for a constant number of queries in the future, or like try and shave off polynomial factors from the polylogarithmic verification. But still, this is really cool. This is kind of what we always wanted. So let's see a bit about how those results came about. So firstly, we should talk about what interactive oracle proofs actually are. Interactive oracle proofs are like interactive protocols between a prover and a verifier, in which the prover sends these proof oracles to the verifier. And instead of completely reading the messages, as in a normal interactive proof, the verifier just has query access to the proof oracles. And then the prover and verifier interact over several rounds. And then at any point, the verifier can make different queries to the proof oracles. And so we can consider queries from different classes. So the three classes that we consider in these two works are point queries. Now, these are pretty easy. In the point query model, the verifier just looks at individual entries of the prover's proof oracles. Another one which is important for us is the class of tensor queries, in which the verifier can ask for structured linear combinations of the messages in the proof oracle, using this tensor product to get the linear combination. And these are like a subclass of the class of linear queries, which has been considered elsewhere. So what happens in the first paper is that we use an approach where we start off with a tensor query IOP, and then we use an interesting code-based compiler, which takes as input also a linear error correcting code. And through this transformation, we convert the tensor query IOP into a point query IOP with sublinear query complexity and verifier complexity. And the main part of the code-based compiler is this sublinear consistency test, with the right query complexity and verifier complexity. Now, let's take a look inside some of those components. So the tensor query IOP that best tensor query IOP that we can come up with at the moment. It works for arithmetic circuit satisfiability over fields of this size, and we have a linear time prover, linear time indexer, a sublinear verifier, and a constant query complexity with these tensor queries. So using our code-based compiler, we'll be able to convert this into the sublinear point query IOP of that first paper that I mentioned. So the thing to note here is that the tensor query IOP we started off with is, well, it just has a constant number of queries, and then things became slightly worse once we moved to this sublinear regime with the point query IOP. We have a sublinear number of queries there. And in some sense, what's going on here is that we started off with like a powerful query class of tensor queries, and then we've switched over to this weak class of point queries. So the verifier needs to do more work to check that tensor queries were simulated properly. We'll see that in a bit more detail later. We can also take a look inside our code-based compiler. So there, this compiler is not just useful for our main result, because it takes a tensor query IOP, and then it produces a point query IOP by combining that tensor query IOP with like any linear code. So like the overheads of the point query IOP that you get in the end depend on like the encoding time and the rate and other properties of the error correcting code. In particular, if we choose like a linear time encodable code as the input, then the compiler is going to preserve the prover and indexer complexity. So using linear time encodable codes is going to be really useful for achieving our main results. Also, we'll see exactly what this means later, but if the error correcting code C has some zero knowledge properties, then it turns out that this compiler will also preserve any zero knowledge properties of the underlying tensor query IOP. Okay, but that compiler that I've stated here is only just good enough to achieve the sublinear result in our first paper, and it doesn't get you all the way to this holy grail. So what if you want polylogarithmic proof size and verification? You need to do something a bit more complicated there. So instead of taking the original consistency test as is, we actually mess around with it a bit and come up with something that's more efficient. So we actually apply proof composition techniques to some of the results in the first paper to improve the consistency test. And this will give us a final point query IOP with much better verification costs and much lower query complexity. Then in order to add zero knowledge to our final result, we need to add zero knowledge first to the tensor query IOP, which turns out to be sort of a standard exercise. And we also need to add zero knowledge to the linear error correcting codes that we use, which turns out to be really interesting. So in this talk, I hope to go over some more of the details of the code-based compiler in particular, and the zero knowledge codes. There are loads and loads of techniques related to our work. So in particular, like it's really closely related to prior works on linear time interactive proofs, different holographic arguments, and then especially different works on code-based IOPs. So the code-based IOPs here, they either give like interesting, general code-based arguments for NP, or like interesting proximity tests for different codes, or one of them in this red circle is a linear time argument. So perhaps the most closely related one is this RR20 work, and that's actually the work that Ron talked about on Monday. So that piece of work has a very similar structure to our own. The main difference being that Ron is trying to be a master of space complexity in that work, and in this work we're trying to really, really focus on time complexity of the prover and verifier. Okay, so before I talk in more detail about any of the techniques inside the papers, I think this would be a good time to pause and ask questions. Answer questions, I'm sorry.
Are there any questions?
I can see that Benedict unmuted himself, but he hasn't said anything yet. So
maybe let me ask a quick question. Do you have an estimate of the multiplicative constant in the prover's running time?
No, we don't actually have an estimate of that. I expect that the main factor to consider there is from the error correcting codes. So there'll be some constant associated with the encoding time of the error correcting code. We're going to use tensor codes, so we'll end up taking taking different functions of that that constant to get to the tensor product. So yeah, I'd say that's the main factor in determining the constant, but we haven't thought about exactly what it might be concretely.
Mm-hmm. And more broadly, do you feel like this approach can be attractive from a concrete efficiency viewpoint compared to the competition?
Yeah, I think so, potentially, at least some parts of it. So I think the interesting thing about the code-based compiler is that it can take any error correcting code as input. So in particular, if you were able to find some really nice, fast code construction, then potentially you could get something really efficient. There are lots of different parameters that you could play with. I think more of a barrier to concrete efficiency is maybe the proof composition techniques that we used later. But yeah, certainly I think there are lots of parameters to play around with. And even if you wanted to use Reed-Solomon codes in the compiler and like lose the linear time, I think there would still be interesting practical things to investigate from this approach.
Okay, thank you.
Jonathan, I have a question too.
Hi, yeah.
So about the zero knowledge aspect, I was just curious if you take, say, your first succinct argument and then compose that with the non-succinct NISC, or yeah, if you're aiming for non-interactive, wouldn't that give you also zero knowledge?
Yeah, that's right. So that would be an easy way to do it, I suppose. I think the reason why we ended up investigating maybe some interesting questions about error correcting codes was we really wanted to do all the hard work information theoretically in the IOP model and get a really nice zero knowledge point query IOP with all the right properties before turning it into an argument. So yeah, I agree with you. I think it it would be easier, and you wouldn't have to consider some of these questions if you went straight to the argument level.
Yeah, so continuing on Ron's question, so if you take the AsiaCrypt 17 paper, what is the time, if the verifier there runs in square root n time, then why not use proof composition to go all the way?
So let's see. That's a good question, actually. It's not necessarily clear to me that that approach wouldn't work and give you something. Just I think at some points when writing these papers, it wasn't necessarily clear that there were good enough ingredients to for like the inner IOP to use for proof composition that would give you something which was still linear time in the end. Actually, it's nice to use this sublinear point query IOP for proof composition because regardless of the polynomial efficiency of what you compose with, you can kind of shrink down the sublinear complexity before composition, and then you don't have to worry about the exact polynomials involved.
I mean, in particular, maybe to add to that, the inner proof system would have to have a prover that is reasonably subquadratic in order to compose it with the AsiaCrypt 2017 paper. And it has to be like not just a PCP or IOP, but it has to be a PCP of proximity or IOP of proximity. And at least my personal belief is such a thing exists, but I don't think an analysis of it has been done, or at least we didn't do it in the BCGT 13 paper. We only did the non-proximity part. So kind of going to like a greater sublinear and starting from a greater sublinear sort of removes this this worry of do I have a good enough inner component, like Jonathan said. That's one point. And regarding the other point about composition at the argument level, it's primarily a question of making a black box result, like with black box cryptography. It's pretty, I don't know. I find it personally complicated to keep track of, are we really linear or are we not linear when you start like dealing with like crypto on crypto. Yeah. So.
Right. So your result makes a black box use of the underlying crypto primitive. So this distinguishes it at least with a naive way of doing the composition, at least at the computational level. So yeah, that's a good answer. Thanks.
Okay, great. So any more questions, or is it time to go on?
Can you guys hear me now? Or? Oh,
Yeah, we are. At least I am hearing you. So go ahead.
Oh, then, well, my question is just, but maybe if it's too long to answer, then you can answer it at the end. But it's regarding the field size. So you said the field size has to be on the order of the size of the statement. Is that correct?
That's right. Yeah.
So, do you think that's inherent, or well, my two questions are: A, whether you think that's inherent, and B, whether you think that you can like maybe pack at least like maybe binary operations, right, or something like that into a large field and achieve something that way.
Right. Yeah, that's a very good question. Yeah, at the moment, I do think that it's inherent. So the reason that we have to use fields of that size is because at some point during the proof, we're using the Schwarzschild lemma and polynomials of degree O of n. And so at the moment, for various holographic parts of the argument, I don't see a way to remove those. And then the issue with packing many different field operations into like single operations in a field extension element is there's some like small logarithmic overhead in the cost of doing like a field extension operation. So if you can't even do too many field extension operations. So I think it becomes extremely tricky.
So if you try to implement a binary field or binary circuit, then it would be actually the cost would be actually n squared, right? Or at least n squared, because you're paying O of n for the field and
yeah, that's right. So I think if you remove the holographic requirement, so if you stop doing the pre-processing and you go back to a linear verification time, then actually the bottleneck comes from a different place in the proof, and like polynomials of much lower degree, logarithmic in n. So that's obviously much better, but it still doesn't tell you anything about constant size fields. So I think I think it would be really interesting and probably quite difficult to get down to constant size fields.
Okay, thanks.
Hi, Jonathan. Quick question. So you mentioned that in this work, you're primarily concerned with time complexity, not space complexity, but are the techniques still amenable to like a streaming style prover, where you don't need to keep the entire, for example, trace in memory necessarily? Or I guess if you're working in the circuit model, you might need to, but I guess you can still like write it on disk and then read it back, or do you need to have the entire thing in memory at all times?
Let's see. That's not actually something I've considered so far. I think that would be a pretty interesting research direction to investigate, though.
Okay, cool. Thanks.
Okay, great. Well, maybe at this point I'll go on and I'll tell you a bit about some of the techniques inside our result. So first, I'm just going to say just very little about the tensor query IOPs. So the main point is that it's very easy to get hold of a tensor query IOP. We have a lot of protocols like the sum check protocol, which are based on the verifier having point query access to the low degree extension of the prover's witness. So we can run a sum check protocol. We know that this can be done in linear time. So this is a good start. And then the main observation that you need here, which comes from Ron's talk and was mentioned in this work on Monday, is that actually evaluations of the low degree extension can be phrased as tensor queries. So the sum check essentially gives you a tensor IOP. And if you want to see that more concretely, you can consider this horrible expression here. So any low degree extension evaluation can be written as a tensor query to the witness. So if this expression scares you, don't worry, you don't have to think about it too much. But the main point is that since the sum check protocol already so easily gives you a tensor IOP, and the sum check protocol can already be computed in linear time and deals with all kinds of NP relations, it's actually fairly easy to get hold of good tensor query IOPs. We did have to do some serious work in the first paper to come up with a holographic tensor query IOP. But there's lots of prior work to draw on this in this area. But perhaps a more interesting part of our work is the code-based compiler techniques, which I'll talk about now. So we're going to start with tensor query IOP. So the prover is going to send different tensor IOP proof oracles to the verifier, who's going to make tensor queries to those. We want to convert this into a point query IOP. So the way we're going to do that is we're going to kind of simulate what happened in the tensor query IOP. So every time, instead of sending the tensor IOP proof message that they were going to send, the prover sends an encoding of that message. And then the verifier can now make point queries to those. So whenever the verifier would have asked a tensor query to one of the oracles, they just send this query straight to the prover, who responds with the answer to that tensor query. Okay. And so we still need to add some extra checks at the end of this kind of simulation process for the tensor IOP. We need to check whether the prover really sent like correctly encoded oracles, which are like good encodings of proof messages. And now that the prover has the freedom to answer the tensor queries by themselves, we also need to check whether the query answers are consistent with all of the encoded oracles. So here we want to choose encodings which preserve linear time and have like good proximity and consistency tests. So I think an interesting thing to note here is that so if you look back at how the tensor query IOP was produced, this was you can easily produce tensor query IOPs based on these low degree extensions, which are like one type of encoding, and then like specifically here we're trying to switch to another type of encoding. So as well as the tensor query IOP to point query IOP, viewpoint, we're compiling from one IOP to another. There's also this code switching viewpoint, which sort of comes from this this RR20 paper that I've mentioned a couple of times. All right, so the encoding scheme that we actually use is going to be tensor code. And the tensor code is based on some base code C. And it turns out that our code-based compiler, it doesn't really need any special properties from C in order to get soundness. The code C just needs to be linear. We do need a bit more from zero knowledge, and we'll get to that later. And most importantly for us is that the tensor code is encodable in linear time if the base code C is encodable in linear time as well. And we've got examples of linear time encodable codes like Spielmann codes or Druckischei codes, which we can use as part of our tensor product codes and come up with like a linear time encodable construction. So I'm about to talk about how the consistency test works. Are there any questions on sort of tensor codes or like the way that the tensor query IOP is simulated? Okay, great. So I'll talk about how the consistency test works. So we've got a tensor query answer, the answer to some query on like a proof oracle pi, and we've also got the tensor encoding of the proof oracle pi. And in order to check consistency between the two, we need to know how they're connected. So of course they're connected by the oracle that was queried and encoded. But we need to look a bit more closely. So first, we're going to see a different way of computing tensor queries from the proof oracle pi. So for this, we're going to define a folding operation. So if we have like 3 arrays like A1, A2, and A3, you can fold with the linear combination V1, V2, V3 just by using the V's to like take a linear combination of the A's. So when you have this folding operation, you can view like the computation of a tensor query as like a repeated folding. So we like first fold by one component of the tensor query, then we fold by the next component, and then we fold by the last component. And this is like a sequential way of computing the answer to a tensor query on the Tensor IOP proof data. Okay, so we can get between the tensor query answer and the original Tensor IOP proof oracle through this folding procedure. Now we have to ask, like, how are the tensor codings computed? So we can build a bridge between the two. So you can phrase the computation of these tensor encodings through these partial encodings. So if I want to produce some tensor encodings, I could encode all of these arrays on the slide like horizontally first, using the base code C. Then I could encode everything vertically, and this would give me the tensor code. So we know that by sequential encoding, we can get from the proof oracle to the tensor code word. Okay. So in order to check consistency, we're going to fill in this diagram a bit diagonally by encoding and folding some of the different components. And the idea behind our consistency test is we want to check consistency at each stage in this diagonal direction. Now, the way that we can do this is by noting that the folding operations and these partial encoding operations actually commute. And so what the verifier would want to check is that these messages on the diagonal, so that when you fold and encode them in the right way, these actually collide and they give equal values. So the proof is going to send these diagonal messages as their point query proof oracles to enable a consistency test. The verifier wants to check that all of these values are equal on folding and encoding, but we need to do this using a small number of queries and with like a low verification cost. So actually, the verifier just queries these stripes of all the different proof oracles, and then the distance properties of the error correcting code actually guarantee that checking only a few positions is enough to find any inconsistencies. So by checking along the diagonal at sort of each folding and encoding step, we can check consistency between like the encoded proof message and the final like tensor query answer. So so one thing I want to say here is that there's, we talked about this nice RO20 result, which is about producing interactive oracle proofs with a very low rate. And we have this work too, which is based on producing interactive oracle proofs with linear time. So those are both of the flavor of like complexity preserving IOP results, and they both use tensor encodings in this very important way. So I think it'd be really interesting to know if there are any other approaches for producing IOPs or any other interesting approaches for producing arguments which sort of don't go through these compiler techniques between different IOPs and don't use any properties of tensor codes. All right, so let's very quickly take a look at the prover complexity of this approach. So if we have if we have like n elements of tensor IOP proof data, then it takes, O of n field operations to actually fold those up. And similarly, if we use like good linear time encodable codes, then the costs of encoding the proof messages to get the tensor code words at the top of the diagram are also going to be linear. It says little o of n, but that's actually a typo. It should be big O of n just there. Now, to compute the other proof messages used as part of the tensor IOP, now at this point, we're already dealing with like folded up tensor IOP proof data, which has size little o of n. So all of the folding and encoding operations that the prover does here, those actually all have a sublinear cost. So none of these operations actually exceed any linear costs. So if we start off with like a linear time tensor query IOP, we don't break anything using this transformation. As for the verifier complexity, since the verifier only looks at these stripes, so in the kind of picture that we've got on the board now, for this example, the verification cost and the query complexity will be O of cube root of n, because the verifier only ever looks at like one dimension of these arrays. Okay, so that was some information on the code-based compiler. Are there any in particular, that's the code-based compiler that would give the sublinear result with the sublinear verification costs and sublinear query complexity. Are there any questions about like different parts of this result or how that works? All right, well, if there are no questions on that bit, then I think next I was actually going to talk about proof composition techniques and how you reduce the query complexity and the verifier complexity of this consistency test that we just described. Actually, since you can view most of the components, for the proof composition as a black box, and these techniques are like relatively standard compared to the other techniques in the paper, I'm actually going to skip straight to the zero knowledge codes part of the talk and talk about how we get zero knowledge in our final construction, because I think, well, personally for me, that was definitely the most interesting part of our paper. Okay, so zero knowledge codes. Okay, so we're going to be using these tensor encodings to encode all of this tensor IOP proof data, and the verifier is going to make point queries to different individual entries of these tensor code words as part of point query IOP, and we need to make sure that the verifier's queries don't leak any information about the witness. So as well as having nice linear time properties and nice like distance properties, our tensor codes also need to have some zero knowledge properties. Okay, unfortunately, this isn't guaranteed from the beginning. If you think about encoding a message using an error correcting code, a linear error correcting code, well, every entry of the code word is actually a sum of message elements. So whichever code word entry the verifier looks at, they're going to learn something about the individual message. They're going to learn one of these linear combinations of message elements. So the way to try and fix this is to choose some elements of the message uniformly at random, add some encoding randomness to the end of the message. And now, if the verifier queries, like for example, the first 3 entries of a code word, then, as long as the verifier can't sort of add and subtract and take linear combinations or do different operations on these code word entries, they'll never be able to get rid of some of these elements of encoding randomness, and they won't be able to learn anything about the original message. Okay, so so far so good. So what we need to do is find a way to study the zero knowledge properties of codes based on the structure of the codes and the amount of encoding randomness that we want to use. And we need to make sure that that is also going to work for tensor encoding schemes. So one technique that we actually use in our paper is to define the zero knowledge property of codes algebraically. So if I write the code word as the product of like some kind of generator matrix multiplied by a message and some encoding randomness, we can ask like, what property of the generator matrix is it? Like what property of the code actually gives you a zero knowledge property so that code words don't leak any information? And if we can understand this for simple codes, this will be a start to understanding something about tensor codes and their zero knowledge properties. So we're going to split the generator matrix into one part that deals with the message and one part that deals with the encoding randomness. Okay, and then we can rewrite the computation of the code word like this with a message part and like this random mask. And now if the verifier queries the first three entries, now the reason that it wasn't possible for the verifier to eliminate the encoding randomness from these first three entries of the code word was because actually no non-zero linear combination of the first three rows of this randomness part will give you zero. So some property of this, the row space of like the randomness part of this matrix. And actually this property has been studied before. So in 2016, Morvais actually showed that no weight B linear combination of rows of this randomness part gives zero. If that's the case, then up to B queries to the code word leaks no information about the underlying message. So this is good. This is interesting. Now we do sharpen things up a bit in our paper. So the important thing here was to consider like linear combinations of the rows of the randomness part of the matrix and ask whether those are equal to zero or not. So if we define the solution space for this linear equation, like all the linear combinations that give zero, we call that like DC, then we know that every element of DC is some kind of strategy which the verifier can use to cancel the encoding randomness from like code word entries that they see and learn something about the underlying message. So based on this characterization, we can understand sort of zero knowledge conditions for code words a little bit better. So if this space DC has like minimum distance b+1, then at most up to and at most like B queries of the code word actually look uniformly random. So this is a stronger property than before, where we just knew that up to B queries leak no information. And I think it's pretty interesting also to know that any B+1 queries are kind of not uniformly random, and maybe they might leak some information. So by moving to this stronger property of like uniform randomness and looking at things in more detail, we were able to like strengthen this condition from 2016 to like a nice equivalence. And then we have like, this is about uniformly random entries of code words. We have like similar results for the zero knowledge property of codes where entries don't leak any information. So I think now would be a good time to pause and maybe answer questions about this. And next I'll go on to talk about the zero knowledge properties of tensor codes. Oh well, this is the coolest part of the paper. I would absolutely love to answer questions about it. So I'm going to persist just for like 20 more seconds, just in case there's a question from an enthusiast. Okay, cool. Well, I guess before I move on, I would just say that one of the reasons I find this result so cool was before I didn't really know say like based on a particular linear code like how to compute something about its zero knowledge properties. The reason I really like this characterization is because now in principle, like given the generator matrix for some code, I can actually like concretely compute its zero knowledge bound, which is not something I knew how to do before. And I can do that using like shortest code word algorithms and stuff from lattice cryptanalysis. And I found that crossover kind of really interesting. Let me go on to talk about tensor products of zero knowledge codes. So the first question here is, if we want to encode a message using a tensor code, how do we add the randomness to the message? I mean, I think when I first thought about this, this wasn't obvious at all to me. Like, how should you add randomness to a message to make a tensor code hiding? Any ideas?
Encode some randomness with the message?
Oh yeah, that's right. Yeah, I guess the question is sort of which format do you want to use? Like, where in this blue square do you want to place the randomness?
I guess maybe around the edge.
Yeah, that's it. Yeah. So yeah, I mean, in one dimension, we have like a message which is in a line, and then we kind of extend the line using some extra randomness. Then in 2 dimensions, we have a message which is a square, and then we just kind of extend with randomness in a square. So so this is a good way to get a zero knowledge property from tensor codes. The nice thing about using this method is that we're still using the original encoding algorithm for the tensor code as a black box. So even though the first paper, the sublinear paper using tensor codes didn't achieve any zero knowledge property, because we could add the randomness in this way, and we didn't interfere with the structure of the tensor codes, we could use loads of results from the first paper as a black box when trying to get zero knowledge. So that was really good. Now, in order to understand like the query bound for the tensor product code, so we have this space DC, which tells you something about like how many entries of the base code word don't leak any information. We need to understand somehow this space D of C cross C. So if you visualize like the structure of this space DC as part of a line, like intersecting with the original code, so we have this space DC, which tells us something about the zero knowledge properties of the base code C. Now, one way to try and understand the zero knowledge property of the tensor product is to actually like draw a corresponding picture in 2 dimensions for the tensor code C cross C. So it turns out that like you can like nicely characterize the shape of this space, for the tensor product code in terms of like the space for the base code. So since we can draw this picture, which tells you that D of C cross C is expressed as like the tensor product of maybe the dual code of C, like tensor product with something else and something else, we were able to get sort of an exact expression in terms of linear spaces for this space D of C cross C. And then this lets us prove something about the query bounds of the tensor product code. So we're able to show that if B queries to the base code look uniformly random, well, we had this equivalence condition, which give us like bounds on the minimum distance of this space D of C. We could show that the associated like tensor product space had like the same minimum distance. And so then up to B queries to the tensor code also look uniformly random. So using these kinds of techniques, we could show that, yeah, also the tensor product code is a zero knowledge code if the base code is. We have similar results for like tensor product under zero knowledge. And in the paper, you can also see a couple of interesting constructions of linear time encodable base codes to use to get our construction. So linear time and zero knowledge, and they're very useful in achieving our main result.
Jonathan, to jump in here, let's try to, I let you run a few more minutes because there were questions along the way, but let's try to wrap up in the next, say 2 or 3 minutes.
Sure. Okay, so that actually brings me to my conclusion anyway. So let me summarize the results that we have. In these two works, in the first work, we constructed a linear time computable IOP, point query IOP, which had any sublinear verification complexity and any sublinear query complexity, but didn't have any zero knowledge property. In the second piece of work, we improved the verifier complexity to polylogarithmic and the query complexity to logarithmic, as well as adding the zero knowledge property. And then using this hashing strategy that we talked about with these special hash functions gives you associated linear time arguments with like the same kind of complexity parameters. And this is sort of exactly what we wanted for a type of holy grail result described at the start. I think the main open question that's left is to do something for smaller fields which have little O of n elements, because there, as I discussed, like in answering Benedict's question, some of the techniques we were using just break down, mostly due to the use of the Schwarzer dilemma with high degree polynomials. So that's like the main open problem that I think remains from this work. So thank you very much for listening. Here again are the two links to two pieces of work, and I'm happy to take any more questions about our results.
Thank you so much, Jonathan. Before people drop off, let me just mention that there are two more and last talks in the afternoon, starting at noon California time. Jacob Lashino is giving a talk, followed by Jing Chen. Yeah, so please come back, and but otherwise, we have a few more minutes now, and in case there are more questions for Jonathan, probably is a good time to do so.
I have a follow-up question to my previous question, if that's okay.
Sure.
So I was asking about kind of composing with another, in order to obtain zero knowledge, composing with, say, a NISC or something like that. And I guess you were saying you'd rather not do that because you wanted to keep things information theoretic, which makes sense. But so why not compose with a zero knowledge PCPP or IOPP or something like
that? That's also an option. I guess the question is then, do we have any sort of off-the-shelf suitable zero knowledge IOPPs or PCPPs with constant query complexity? Potentially that would work. It was convenient to use this kind of off-the-shelf result we had, which didn't have any zero knowledge. Actually, we did investigate this approach, and also in our paper, we sort of studied very carefully, facts about the zero knowledge properties of IOPPs under composition, like what happens when you robustify with the zero knowledge code and stuff like that. So although we didn't go down this path, we did investigate like some of the like formal zero knowledge properties, like that would stand you in good stead if you did try to follow that alternative path.
But so you eventually get, if I'm not mistaken, you get polylogarithmic query complexity. So actually, zero knowledge PCPP with like a polylogarithmic query complexity would suffice. Is that right? Zero knowledge. Right. I see.
Yeah.
Okay.
That's actually, I guess there's a technical point there. So, strictly speaking, we have this consistency test, which is used in our compiler, which has like sublinear query complexity and verifier complexity. And we apply proof composition to that. There are some other there's some other logarithmic communication costs, which are not part of that consistency test. So I think if you wanted to try and get like a constant query complexity, you could try doing proof composition on like the whole proof system rather than just this consistency test part, and then you might see something a bit different as well.
Mm-hmm. Okay, thanks.
Does the folding operation affect zero knowledge? Like, do I have to do something to stop this from leaking information?
Right. So what we actually do is, as part of the Tensor query IOP, and somewhere in the code-based compiler, we produce these big masks. So every time we have like a Tensor IOP proof message, we compute like a random mask of the same size, and then using these masks, we kind of run the compiler and the consistency test on values which have already been masked. So so the values which are being folded up are these values which have already been masked. So like the smaller arrays that I was showing in the slide, like lower down in the diagram, they don't leak any information at all because they're kind of like folded up things which have already been masked. It only sort of matters at the top. So when you want to make a query to the original masked, so the biggest masked message, well, this is a sum of like a Tensor IOP proof message and like a mask. You only have to worry about things at the very top, and then that information is protected by the Tensor encodings.
An interesting point related to masks has to do with rate. So unlike Ron's work, where you can use these tensors in a very careful way to get the rate close to 1, provided that also the code you start with has really good rate. Just because we have these masks flying around to mask this and that query, these are extra code words that are being sent that sort of are on top of the encoding of the kind of computation. And so these by themselves already, they give you a sort of rate that is bounded away from 1, in fact, quite away from 1. Now, like other applications of zero knowledge, probably they can be de-randomized if you kind of very carefully sort of sprinkle randomness in a white box way through the corresponding protocols. There's like something similar can be done with some check and GKR, right? So, but sort of achieving simultaneously kind of zero knowledge, linear time, and rate close to 1. I think that's also another question because kind of rate and zero knowledge, they're kind of in tension there. When you want to mask blind things, you want to send extra code words, but rate close to 1 prevents you from doing that. So you have to kind of de-randomize things. It's a nice question there.
Ale, if you follow the kind of idea of composing with the zero knowledge PCPP or IOPP, say you start off with, if you had something that was not zero knowledge with a linear time prover and succinct proof, and then you compose with a zero knowledge PCPP or IOPP, then it seems to avoid all the masking business.
So it's not clear kind of what happens in that case for the kind of zero knowledge part, right? Because kind of the outer proof system, which I guess in your example is not zero knowledge. I mean, you're sending the oracles; they really are there, right? So
you're right.
Right. Now,
right.
I know that one can consider some weak notion of zero knowledge that maybe you can then make up for it in different ways. But, this type of composition is not super nice for zero knowledge, right?
I agree, Mitanas.
Now, again, there are other natural properties of zero knowledge that are preserved in proof composition and robustification. It's something that in some earlier iterations of the protocol we were actually using. Then we didn't end up using them, but they're so cute and natural that we stashed them in an appendix somewhere because they definitely look very interesting. So you can ask, in standard sort of proof composition of outer and inner, or standard robustification IOP, what happens if either of the components have a zero knowledge property? What happens to the resulting thing? And it turns out that sort of natural definitions for the ingredients lead to natural sort of conclusions in the output. And so that's something that we look in rather carefully in two appendices.
Okay, thanks.
I have a question to Jonathan and Alessandro about the polynomials you use when you use the Schwarzschild lemma. I'm trying to understand why you need the degree to be that big. Like, how many variables do you have in a polynomial? Like, would it not be possible to sort of bump up the number of variables and to just basically lower the degree of the polynomial and then still be able to apply Schwarz simple without caring?
Right. So the issue there is that part of the argument, if you think about how various different shuffle arguments work, if you want to show that one collection of n elements is like a permutation of another n, you can show that like some degree n polynomial, which has elements on the left-hand side as roots, also has like the same roots, which are elements on the right-hand side, and then you show that kind of one set is like a permutation of the other. So we have polynomials which look something a bit like what you see in the shuffle arguments. We have a more concretely like a lookup protocol which uses polynomials of this type. So we have a degree n polynomial in one variable, for example, and I'm not aware of like any strategy, for example, for like permutation arguments, which will lower the degree of the polynomial, but still give you nice properties like a polynomial of which will still say something about like the roots of the polynomial on the left-hand side, same as we have the same values as the roots on the right-hand side, like both corresponding to the same polynomial. I just don't know how to do that with like more variables and like a lower degree.
Okay, I see. Thank you very much, and thanks.
Any more questions? Great. So I think thanks to both Benedict and Jonathan for a great pair of talks this morning. Also, thank you very much for the live attendees for the excellent questions and interesting interactions. So now there's a break and we'll resume in I guess 55 minutes for the two afternoon talks. Talk to you later.